So please, Balazs.
Thank you very much, and thank you for the invitation. So what I would like to talk about is a joint work with anti-cane monkey. But before I turn to the talk, I would like to describe you what the superexponential condensation and exact overlap mean and why is it an interesting question. So I would like to give you a little background in the theory of self-similar systems. So what are these self-similar systems? Well, take a finite collection of contracting similarities on the real line. Now we will almost every time we'll be on the real line. So it's a, but most of the things I say is true in higher dimensions. So what do we have? We have a contracting ratio lambda I, which absolute values between 0 and 1, and some translation. We have finitely many of such functions. Then it's of course easy to see that you can find a large number R such that the interval minus R, so a huge neighborhood of the origin, is mapped into itself by all the maps, all the contracting maps. And then this means that if I take all the possible iterations of these similarity mappings, so this is all the possible iterations of n functions, and apply to B, B is a closed set, then this is in n a shrinking sequence of closed sets. So the intersection will be non-empty and compact. And basically, this is how you construct a self-similar set. Why do I say that this is self-similar? Because if you look at this formula, then it's easy to see that this X set satisfies this equation. Namely, it will be a union of similarity copies of itself, finite union of similarity copies, and that's why we call it self-similar set. And moreover, this guy here is the unique non-empty compact set, which satisfies this equation. So basically, also you can define something that's similar as measures. So you take your favorite probability vector, then also you can construct a unique and compactly supported measure, which is invariant, namely the measure mu is the weighted average of its push forwards via similarity maps. So this phi I star means the push forward of my measure mu. So in the same sense that the X is the union of its copies, then mu, the measure, is a union of its, is a sum of its weighted averages of its copies. And we call these measures self-similar measures. So these are objects we would like to study. And basically, one of the questions is to study how large these self-similar sets can be. Of course, the large, think about an example is the triadic Cantor set. I think everybody very much knows the triadic Cantor set, which is all the points on the interval which triadic decomposition contains only 0 and 2s. And this is a self-similar set by the scaling 1/3 and 1/3 plus 2/3. But of course, and we know that this triadic Cantor set has 0 Lebesgue measure. So how large means in our sense is how large in the sense of dimension. So, and this sense is usually the Hausdorff dimension. There are other type of dimension, of course, in the business, but for us, the most important is the Hausdorff dimension and the Hausdorff measure. And let me tell you, just briefly recall what this measure is. So if you are taking the delta approximation of the S-dimensional Hausdorff measure of a set E, means that you take all the covers of the set E with sets which has diameter smaller than delta, and you take the infimum for the sums of the diameter, so from this cover to the power S. So then from this definition, it's clear that for UI, you can think about that these are balls, open balls. So then the S-dimensional Hausdorff measure is that you take the limit to delta to 0. The limit exists because this guy is a monotone increasing sequence. So basically, the question is, how can you cover optimally a set E by sets in the sense that the sum of the diameters of the cover to the power S should be the smallest. It's the most smallest possible. And the Hausdorff dimension is telling you that what is the smallest quantity which makes this set visible via the Hausdorff dimension, namely the smallest S for which the S-dimensional Hausdorff measure equals to 0. Similarly, for measures, you can also define the Hausdorff dimension. Sometimes this is called the lower Hausdorff dimension. Namely, you take all the Hausdorff dimension of the sets, the smallest one, which is still visible by this measure. By the smallest one, of course, I mean the infinite. So in the case of self-similar measures, there is, well, one hand naive, other hand natural upper bound, a natural cover provided by this construction, right? Because this X is this huge intersection, then for every n, this union here will be, of course, a cover for my self-similar set. Of course, the diameters of each of these sets here can be chosen to be arbitrarily small, since we have contractions. So basically, what we say is that we choose n so large that the diameter, and I introduce a notation. So if I take a finite word made of the symbols corresponding to the functions, then by phi I denote the composition of these maps in the order of the symbols, phi I1, In, and also by lambda I mean the product of the symbols of the contracting ratios, lambda I1, lambda In. So if I choose n so large that the diameters of this phi I of b's are all smaller than delta, then of course this is clearly an upper bound. And since these are similarities, then what happens is that the diameter of phi IB is just a scaling by lambda of I, right? And then since we took here all the possible n-length words and the products of all the possible n length, then this is just the nth power if I just take the sum of the contracting ratios to the power S. So it's clear that if I choose S in such a way that this sum here is smaller than 1, which clearly can be done, since if I just increase S, then this guy goes to 0. So if I choose S so large that this is smaller than 1, then this just simply goes to 0, and we have an upper bound for the dimension. And so what is the upper bound? The Hausdorff dimension then is at most the dimension of the state space. Of course, the dimension of the line is 1, and this S naught, which is usually called the similarity dimension, and it is the unique solution of this equation, namely you take all the contracting ratios, take to the power S naught, and solve it to be equal to 1. And this is true all the time. So this is an upper bound. But this upper bound is sharp in the sense if you have some separation between the images of the self-similar set. Namely, Hutchinson showed that if you assume that if you take the images of phi of x by different maps, phi I and phi j, and they are disjoint, then actually you have equality here. So the Hausdorff dimension will be exactly this S naught quantity, exactly the similarity dimension. Actually, he proved more, but for us, it's absolutely enough. So how to show such thing, this separation? Basically, if you find a measure which sees this set, namely it gives it positive and finite measure, and you can provide also that there is some constant C, such that no matter what kind of U set you take, the measure of U is at most constant times its diameter to the power S, then the Hausdorff, S-dimensional Hausdorff measure can be bounded below by this factor, which is strictly positive. And then, since we are looking for the values which are giving, the infimum of the values for which this quantity is zero, then this S will be clearly a lower bound. So this is an easy observation, by the way, but this is called also the mass distribution principle. So this is because if you take any open cover, not just any cover of X, then this sum, of course, using this inequality, can be bounded above by the sum of 1 over C times the measures of these sets from the cover. Of course, the measure is sigma subadditive, so this is the union, and since it's just a cover, this is still at least the measure of X, and this guy is positive. And no matter what cover I took, this inequality still every time holds, so it must hold for the S-dimensional Hausdorff measure as well. Nice question, how to construct such kind of measure? Well, one way is to construct in self-similar cases self-similar measure. So let me construct this self-similar measure, what we have seen in the following way. So take all infinite sequence of symbols which are corresponding to these functions. And you can define them by using the construction a nice Hölder continuous mapping from sigma to X. How? You basically take your infinite word, I, this is now an infinite sequence of words, you restrict it to the first n symbol, look at where this B set, which is mapped into itself, is mapped, take the intersection, and by you have contraction, this will be just one point. And on this sigma space, it's more convenient to define measures, since here I can define a measure as follows. So take the set which first n symbol, so take the set of those infinite sequences which first n symbol I1, In, J1, Jn equal to some pre-given fixed I1, In values. And you say that the measure is just lambda I1 to the power S naught times lambda In to the power S. So this basically means that you define a random distribution on these infinite sequences as follows. You take a coin tossing, several side coins, but it's okay. Each of the tosses are independent, and the probability that you choose the symbol I1 corresponds to lambda I1 to the power S. So this is how you construct your measure, and by using this capital pi, you push forward it to the similar set. So then, this is the measure what we are looking for. Because if you take the measure of any set U, then its measure can be bounded above by the measure of those finite words for which the corresponding image intersects the set U, and also you can say that at the measure and the length, the diameter of this set is corresponding to the diameter of U up to some uniform constant. So basically, since all these quantities here are comparable with the diameter of U to the power S naught, then basically you count here how many such kind of symbols you have. And by this separation property here, you can show that there is only finitely many. So only just finitely many such kind of sets can fit into any set. with diameter u. And this is good because then this constructs you, this gives you this uniform C constant, and this constructs you the mass distribution, and it shows that this S naught is indeed also a lower bound for the Hausdorff dimension. But of course, it's a large set where you might have separation, but what happens in other cases? So also Hutchinson showed that if you take just general measure, a general self-similar measure with general properties, not specifically corresponding to this lambda I S naught, but also arbitrary probabilities, but you still assume strong separation, then its dimension is entropy over the Lyapunov exponent. Entropy is just the usual entropy of this probability vector, and the Lyapunov exponent means basically the average contracting factor at a typical point. So these are the natural values, and in each of the cases, these S naught and this entropy over Lyapunov exponent value is an upper bound for the dimension. So we say that the dimension drops with respect to these natural value if, of course, the dimension of X is strictly smaller than this natural quantity what we had. So the minimum of 1 and S naught, where S naught was the similarity dimension. Or we say that the dimension of the self-similar measure drops, again, if the dimension of this measure is strictly smaller than this natural quantity what we have seen, the entropy over Lyapunov exponent. And of course, I need to add here the minimum of 1 because the dimension of anything cannot be larger than the dimension of the state space. So if we have strict inequalities with respect to the natural upper bounds, then we say that the dimension drops. So how can you achieve dimension drop? Basically, if you choose functions in the generated semigroup of the similarities, namely, if you can find two different iterates corresponding to different symbols of the functions, such that they completely agree, completely coincide, then you can achieve dimension. So if you choose, you need to choose your contracting ratios in such a way that their sum is strictly smaller than 1. With basically, this provides you that the similarity dimension is also strictly smaller than 1. Why is it true? Because, of course, this phi I is the iterated function system corresponding to X. But it's all iterates in an iterated function system with respect to X is self-similar. So what do? This is my equation, right? This is S naught, the solution of this equation. And if I take the nth power of this guy, well, it still must be equal to 1. Okay, and then also this is the sum of all n-length words of the contracting ratios lambda I corresponding to the n-length words to the power S naught. Now, if there is some word J, and there is some other word with length n, such that phi I and phi j completely agrees, this means that the two maps is exactly the same. So I actually don't need one of these maps. So I can just remove this j, and I got here a strict inequality. And still, with respect to this smaller iterated function system, in the sense that I remove the function which corresponds to j, this will be still a self-similar set which corresponds to this, which with respect to this set is invariant. But the strict inequality means that using this, we will get still a natural upper bound. So if you solve this, the equation that this quantity here needs to be equal to 1, which means that I need to decrease strictly the value S naught, then this will be still an upper bound. That's why the Hausdorff dimension drops in this sense. And But the folklore conjecture claims that basically this is the only way how to achieve dimension drop, and there is no other method. There's no other known method. So basically the dimension drop conjecture says that the dimension drops, so these inequalities are strict, if then there must be an I and j finite words which are not equal symbolically, but the corresponding functions completely agree, is exactly the same. So a seminar paper of Hochman made a nice step forward in the direction of proving this conjecture. What he showed is the following. So let us define a function on the pair of finite words bi, bj, I and j in such a way that if the corresponding contracting ratios lambda I and lambda j are the same, then let's take a look at the distance of phi I naught and phi j of naught. Basically, this is the distance of the translation parameters. Otherwise, if the contracting ratios are not the same, I don't really care about these guys, so I just simply say that the distance is infinite. And take capital delta N, which is the minimum of the distances of the symbols I, j, in this sense, different words of length n. And Hochman showed that if the dimension drops, if you have strict inequalities here, then this delta n factor goes to zero extremely fast, namely it goes to zero super exponentially. See here, take the logarithm, divide by n, then this goes to infinity. So in this case, we say that if this holds, we say that there is a super exponential condensation. And our problem is the following. So a natural question is, okay, we have this corollary that the dimension drop, then we have super exponential condensation. Then a natural question is that, is it possible actually to have this super exponential condensation, super exponential closeness between the cylinders actually without having exact overlaps? So this is the purpose of our study. Why is it a question? Because Hochman also showed that if all your parameters, the contracting ratios, lambda I, and the translation parameter ti's are algebraic numbers, then the super exponential condensation between the cylinders must mean exact overlap. This theorem was extended by Rappaport, and he just assumed that the contracting ratios very recently, So he just assumes that the contracting ratios are algebraic, and he proved that if there is a dimension drop, then there must be exact overlap between the cylinder sets and between the functions. And also there is another result by Varyu, who says that if you take the special system where you have just only two functions, lambda x and lambda x plus 1, which is called the Bernoulli convolution, and you take the probabilities 1/2, 1/2, then the Hausdorff dimension of the corresponding self-similar measure will be every time 1 if you choose your contracting ratio lambda to be a transcendental number. Of course, here the lambda needs to be chosen to be greater than 1/2. So in this case, the attractor, the self-similar set in this regime corresponding to this iterated function system will be all the time an interval. So it's not a question that will there be a dimension drop or not. But the measure with probabilities 1/2, 1/2 can have dimension drop in this situation. And Barany showed that if you choose your values to be transcendental, then it's not possible. And of course, it's easy to see that all the phi I zeros for any finite words are just polynomials, integer valued polynomials of lambda. So basically, you can achieve exact dimension drop and exact overlap only in the case when lambda is algebraic. So basically, a corollary of theorem of Barany says that for these Bernoulli convolutions, the conjecture, the exact overlap conjecture, what we have seen, holds. But unfortunately, we will show, or fortunately, I don't know which one is better, but we will show that it is possible to achieve this super-exponential condensation without any exact overlap in the system. And we will be looking for it in this following special family, lambda x plus t, lambda x plus 1. So we have just two parameters. All the functions has the same contracting ratios lambda. And we choose lambda to be between 0 and 1/3. And we have one translation parameter t, who we will choose to be between t and lambda over 1 minus lambda. Why we choose it in such a way? So if you are looking at these three functions carefully, then it's easy to see that the interval 0, 1 over 1 minus lambda is mapped into itself by all the maps. Moreover, the image of, so phi 1 has fixed point 0 for sure, and phi 3 has fixed point 1 over 1 minus lambda for sure. And we choose this t parameter to be smaller than lambda over 1 minus lambda in order to achieve overlaps at most between the cylinders corresponding to the first and the second function. So we don't allow that the second and third have overlaps in between them, and phi 1 and phi 3 clearly, because of this 1/3 bound, won't have any overlap. So this is why we choose, and let us see three subsets of this set of parameters. Namely, first, the E, which says that we put here all the parameter pairs, lambda and t, which has exact overlap. In D, we put all the values of parameters, which has dimension drop. And for C, we put all the pair of parameters such that whose are super exponentially condensated. So we have seen the following inclusion chain. So of course, exact overlap, as we have seen, must be contained in the dimension drop set. And Hochman showed that the dimension drop set must be contained in the set C, the super exponentially condensated set. And our result with Antti Kaimäki says that if you are looking at the set C minus E is actually uncountable. So this is the main result of us. What we know about the super exponentially condensated, so what we know the dimension relation here is one hand due to Hochman, who showed, okay, I wrote here p-packing dimension, but just think about the Hausdorff dimension, what we were discussing so far. So Hochman also showed that the set in this two parameter self-similar system is at most 1, where they are super exponentially condensated. So for the remaining two-dimensional part, it's not super exponentially condensated. And in the recent result of Rappaport and Barany, they also showed that if you take the difference of the dimension drop set and the exact overlap set, its dimension is at most 0. Why am I saying that at most 0? Because it might be possibly an empty set, and an empty set, it's, well, depends on the convention, of course, but I like to think about the empty set to have dimension minus infinity. So basically what you have, what they showed here, that even if this set might be non-empty, but if it's non-empty, it's still a relative, it's a very small set in a sense of dimension. Okay, so in the rest of the talk, I would like to focus on this result with us with Antti Keinmäki. But before to mention that, I need to mention that recently Baker and also Chen showed something very similar. So Baker showed independently of us using different methods that if you took here this iterated function system of similarities on the line, you have 6 maps here. All the maps has contracting ratio 1/8, and you only have some special relation between the translation parameters. Then you can choose, there exists a pair of S and T here in such a way that this system is super exponentially condensated, but there is no exact overlap. So what is the advantage of Baker's result? The advantage is that by combining it with Rappaport's result, who proved the conjecture with algebraic contracting ratios, that indeed you can find a system on the real line, which is super exponentially, sorry, a super mean is missing here. So, which is super exponentially condensated, but there is no dimension drop. So this makes clear that the super exponential condensation is not a good way to characterize the dimension drop. And basically Chen's result restricted the number of functions here into 4. So you can also have 4 functions.
Okay, just so is it right that the difference is that in your result with Antti, lambda was not algebraic, right? And here
lambda is absolutely not algebraic in your system. Actually, it must be very transcendental, I think.
Okay.
Yes. So yeah, Boris, you're right, because this indicates a question whether it's possible to construct such systems with 3 maps only, and you have algebraic contracting ratio. And I believe that it might be not possible. Okay. So let's turn back our system, because in the remaining, let's say 20 minutes, I would like to tell you some ideas about the proof. So this is our 3 maps, lambda x plus p, lambda x plus 1, and this is our parameter space. We are in between 0 and 1/3, and the translation is between 0 and 1/1 minus lambda, which means that there is possible only overlap between the phi1 and phi2. So if you choose your parameters in such a way that there is some overlap between the cylinders, then you can be sure that one of the maps must be indexed 1, other guy must be indexed 2, or well, 2 or 1. And also easy to see that if you take the iterates of these maps, then phi I for this finite word can be written as lambda n times x plus this nice sum, where this delta is 1 if the kth symbol equals to 3, and this delta 2 equals to 1 when the kth symbol equals to 2. In any other cases, it will be 0. So basically, the translation parameter phi I of 0 is just a polynomial of lambda, where the coefficients are just 0, 1, or t. Okay, so what is our goal? So take your favorite and very favorite monotone decreasing sequence in such a way that it goes to super exponentially 0. This is indeed your favorite, so whatever you can choose, as quick as you wish. And what do you want? What you want is, if you take 2 different words, and we want to be sure that these words are different, which means that we just assume that the very first symbols are different. And we want that the translation parameters corresponding to these words I and j are very close, these eta n super exponentially close to each other, then using the previous form, which says that these guys are basically just polynomials of lambda, we can write it in this form. And now this part here, so this is now actually a polynomial of lambda minus t times another polynomial of lambda. This just depends on the symbols, whether or equal to 3 or not. This depends on symbols, whether equal to 2 or not. And by the choice of 1/3 here, this polynomial, regardless of n and anything, will be comparable, will be between 1/2 and 2 all the time. So basically, up to a uniform constant, this is the difference of t on the ratio of these two polynomials. And this is the importance for us. Why? Again, why is it comparable? Because at k equals to 0, so the very first symbol, here the value will be every time 1 or minus 1. This is how we were choosing the overlap structure. Okay, so basically we would like to analyze these ratios, how these ratios are behaving. So basically you have pairs of symbols, right? Lambda and lambda, because this is ik, jk, jk, ik. So we are mapping the pair of possible pair of symbols, 1, 2, 3, 1, 2, 3, to another symbolic space psi in such a way that if you see the pair ij, then you take here the difference delta I, delta j, which corresponds to the nominator's coefficients, and here delta j minus delta I of 2's, which corresponds to the denominator's coefficients of lambda. Okay, and it's easy to see that these are the only possible values. And basically, this system is very natural to represent it as a self-similar system on the plane. So you take an iterated function system on the plane as follows. For each pair ij, and now these ij pairs are from this psi, so they can be just 0, 0, 1, 0, and so on. And you take the functions lambda x plus I, lambda y plus j. Okay, so basically here in this picture, what you see here, these gray smaller squares are just the images of these large square according to these maps. Okay, and basically this green guy, what color is it? Blue guy here, this blue hexagon is basically the set which is mapped into itself by all the maps in this psi set. Okay, so then basically what are you interested in? What we do is that this set also, this iterated function system here constructs also a self-similar system, a self-similar set, but now on the plane. And what we do is actually, we take the projection of the cylinders 1, 0, and 0, 1, and 0, minus 1 in the sense of slope. Okay, why? Why only the 0, 1, 0, minus 1? Because we agreed that the overlap can happen only if you have pairs in the original systems 1, 2, or 2, 1. And with this mapping, this will be every time 0, and this must be then every time plus or minus 1. So this is why we focus only on these two parts. And why the slope? Because basically here, what is this? This is the x coordinate of the nth iterate of my function, and this is the y coordinate of the nth iterate of my functions. So this means basically that it's absolutely enough for us to show that there exists a sequence made of symbols in Xi, such that it begins with 0, 1, in such a way that the projection, this nonlinear projection, which gives you the value of the slope x over y of the iterates of these S maps with respect to this Kn, will be super exponentially close to this P. And this is perfectly fine for us to show that. And there is a technical lemma which allows us to do so. I won't prove this technical lemma, but I would describe why is it important for us. So you can find finite words with length 5, but any finite words, such that they are different. Although they are different, both first symbols here are 0, 1. And the following properties you will have for any other finite words, which begins, so the first five symbols of K and H will be these K1, H1, such that for every lambda parameter value between 1/4 and 1/3, the following holds. This nonlinear projection depends transversally on lambda. Namely, so these are, of course, nice functions, nice smooth functions in lambda, but you can ensure that their movement is quick. So the difference between the speed of this function and that function in the sense of lambda is strictly different. Namely, if one hand, for some values, they are close to each other, then using this transversality, you can be sure that they will become far from each other very quickly. On the other hand, they are geometrically also a nice symbols. Because if you take this attractor, so the attractor of this system, what we have seen, the self-similar set defined by these S maps, then the projection with respect to this nonlinear mapping will be intervals. And these intervals has nice structure, namely this will be, this at 0, 0 values will be the center of the intervals, and the length of the intervals will be lambda to the power, the length of the finite words. So these are very, very nice geometric intervals. Moreover, and this is also important, you can find the lambda star inside this 1/3, 1/4 interval, such that these two values, so the projection of the iterates with respect to H1 and K1, so these centers are equal. So all these properties will be extremely important, but let me tell you why. Because using these three properties, you can construct a dyadic chain of intervals and a dyadic chain of finite words in Xi in the following way. So this is just an auxiliary dyadic chain. This is not really a dyadic chain. This is just some sequence of symbols. But this is indeed a dyadic chain here of closed intervals. Why? Because each of these intervals here, corresponding to some edge in the tree, we have length eta of the length of I omega, the finite word in this auxiliary tree. I omega is contained in all the time in its parent, and the siblings, I omega 1 and I omega 2, will be disjoint. Moreover, for every interval in this I omega, you can make the following relation with these finite words in I omega. So if you are looking at what's the distance of this projection of I omega from its parent, will be at most some constant times where this constant corresponds to this transversality constant, at most eta at the length of I omega, but the distance of I omega from every finite word which has length, at most its parent's length, is at least delta times eta of length I omega. This guy here, this upper inequality, is responsible for us to construct the superexponential condensation. And this guy here down, who is responsible for us to say that there will be no exact overlap. Okay, so assume first that we have these properties, then how to construct these parameters where we have our prescribed properties. Well, first, what is this? This is, of course, a nice Moran construction. Namely, I omega is a decreasing sequence of words, of closed intervals, right, in n, in the length of omega. So therefore, its intersection is non-empty. Moreover, by this disjointness property, you can be sure that for each omega, there is one unique, so it's a one-to-one map, which maps this infinite word of 1-2s to the interval 0, 1/3. There will be only one and only one. Moreover, we define the translation parameters by taking this limit. So you just take the auxiliary I omega symbol restricted up to n. The contracting ratio, what you need to use is what's defined here, and you take the limit. And what I claim is that since this disjointness, there are uncountably many such contracting parameters and such translation parameters. But on the other hand, this has all the properties what I want. So first, if you want to use this property, then how can you show that? Take your favorite m, and you choose n in such a way that m is in between some parent and the length of some parent and some children. This is how you choose n. Then, in order to get a word with length m, I just extend this I omega n minus 1, the parent, with zeros, 0, 0 pairs at the end to get length m word. And now I'm looking for such words km and hm in the original symbols with length m, such that the beta map, which takes this difference between the delta 3 and delta 2s, will be equal to jm. Of course, this is not a unique mapping, but I don't care. Take your two favorite. And what I claim is that km and hm symbols, these guys, are super exponentially condensated. Why? Because if you take phi km and phi h of m at 0, then we have seen it that it's up to a uniform constant, more or less the difference of t and the projection of s. Yeah, and here, because here you got some beta m here, so this is the beta of km hm, which has to be fixed as jm. But since the very last symbols of this jm were zeros, which means that the coefficients, the largest coefficients at the end on the numerator and the denominator are zeros, basically this ratio, this projection of sjm, is just the projection of I omega n minus 1. This is because the last coefficients are zeros, so you just neglect them. And also, this k omega here is just this limit. So of course, I can just take the difference, take the upper bound of difference and t with this projection I omega up to n minus 1 with this infinite sum, where you take the differences from n minus 1 and n, then n plus 1, and so on and so on. And we know by construction that these guys were super exponentially close to each other, which length corresponds to I omega L, the children here. And here, in this infinite sum, if you use the super exponentiality, then you see that this guy here, since you have here strict inequality, and the smallest length of these words corresponds to I omega n, if m is sufficiently large, then this is at most eta, this sum here, this whole sum here is at most eta m. This is by super exponential. So these two guys are indeed super exponentially condensated. And how do we know that there are no exact overlaps? Well, suppose that there are some exact overlaps. So you can find finite words, and without loss of generality, you can assume that they have the same length, such a way that they agree at translation parameters. And of course, they agree for contracting ratios. Then again, the difference of phi k of 0 and phi h of 0 is the difference of t omega and the projection of s lambda k beta of kh. Right? This new symbol in the new symbolic space psi. But now you choose n in such a way that even the parent I omega n minus 1 is longer than n. Why? Because then this difference clearly can be bounded by below with this infinite sum. And why is it good? Because this guy here is what? This guy here, what we know by this property, is at least has the difference I omega n, delta times I eta omega n, right? Because this beta has length m, which is shorter than its parent, and here you can put any word which is shorter than the parent. Right, so this is the lower bound here, and the upper bound is exactly the same like previously, using the super exponentiality. This is 2 delta minus 1 I omega of n plus 1, since every time you are taking here as an upper bound the longer guy. But using the super exponentiality, this is strictly longer than this one. And since this is strictly longer than this one, plus the super exponentiality immediately mean that this guy here is positive. So contradiction, there cannot be exact overlap. Okay, I also wanted to show you how to construct these intervals omega by using the technical lemma, but I think I'm out of time, and this is the perfect place then to stop. So thank you very much for your attention.
Very much. Thank you very much.
Thank you.
Are there any questions or comments? So in your examples, do you expect that there is dimension drop or not? Or how difficult?
Well, I would think for this example, for this particular system, I think that the dimension of conjecture holds. Mm-hmm. And I think that also Ariel Rappaport and Peter Varju are very close to show that. Mm-hmm. But I'm a little bit suspicious for more functions, actually. So somewhat similar constructions can be made, and then you see that there is more and more space to do nesty things. So so I think for this special system, the dimension drop conjecture holds, but it seems that there are more interesting things are going on for if you take more and more functions.
Hmm. Any other questions? Okay, if not, thanks the speaker again.
Thank you.